Okay, so we just talked a little bit about slope and how slope is really the 8th grade or algebra term for unit rate. And so we're going to use that concept of unit rate to dive a little bit deeper in here. So let's take a look at this example. JJ mows lawns for his dad's company. He has been paid $50 to mow 5 lawns. What is the unit rate for 1 lawn? So that's actually a pretty simple problem. So the first thing I want you to think about is when you are starting to think about this, the hardest part is for kids to remember or know even which number to divide by which. So here's how you're going to think about it. Am I trying to find the number of lawns per money or how much money per lawn? So I really want to take the amount of money that he makes and divide it by the number of lawns that he, we'll put lawns for that. The number of lawns that he cuts, okay? And that is what's going to give us here. So he made $50 for 5 lawns, which means I'm going to divide and I'm going to get $10 for 1 lawn. And if you remember writing it, that is how it looks in terms of unit rate. The denominator is always 1, but we're just going to keep that as 10 right now. So the rate per lawn is $10. So let's see what that looks like over here in the table, because we're going to make a big connection between the description, the table, the equation, and the graph. That is what this whole next couple lessons are going to be about. So let's think about this. If it's a lazy day and JJ doesn't go out and mow any lawns, how much money is he going to make? Nothing. Big fat nothing. So let's say he rakes 1 lawn. We know by now, because we figured out the unit rate, that he's going to get $10 per lawn. So after he's mowed 2, you guys, we can just kind of cruise through this. He's going to make $30, and for 4 lawns, he'll have made $40. Okay, and the next point would be the 5 and the 50, right? So nothing new and crazy about that. Let's take a look then. It makes the most sense to go right from a table of values directly to a graph. So you know, when you make a table of values, what that does is it gives you your coordinates. So I could take each of these points and say 0, 0, 1, 10, 2, 20, okay? And then what we're going to do is we see that we have the number of lawns is going to be, this is your independent variable down here. The money depends on how many lawns. So your Y value is almost always going to be your cost. And so let's take a look at this. If I don't mow any lawns, I don't make any money. So I'm going to put a point right at the origin. Okay, I don't know if you can see that or not. And then after I rake my first lawn, I've made 10, and my second lawn is 20, and so on. And so I could just keep going and going and going. And then if I follow this line out, I could see, well, if he mows 8 lawns, then my line's off a little bit, but he should make $80. Okay, so that's what the graph of that looks like. And so let's talk about this equation, and the equation is actually easier to get from looking at the table. We learned this before, that looking at that, it says here that you told me actually last time we did this, that every one of your Y values was just your X value times 10. So you told me that all of the Y values are equal to 10, the X value rather, times 10. Okay, and so we are going to take a look at this equation in the form of Y equals mx. We use m, that stands for slope, right? We learned that. It's actually a French word, monter, which means to climb, which we learned as rise over run. So if I were to take this and say he's earning $10 per lawn, this is what it looks like for JJ's situation. So we took this 10 and we've solved it from our unit rate, which we took, and take a look at this, and 1, 10, which means the 10 is here, and the 1, 10 is here, okay? So let's take a look at this next example. Do this a couple more times, because what I'd like to do is see if we can come up with a discovery of how this works on our own without me just coming right out and telling you. So let's zoom in a little bit here and let's take a look at this next example. Let's say you babysit, you're not getting paid very much, you're getting paid $5 an hour. That's okay, it's still good hard-earned money, right? And I want you to take these words and turn them into a table we're going to write the equation, and we're going to graph it. And then we're going to take a look and see what they all have in common. So let's say that if X is the number of hours, because this is our time, X is almost always time, it's the independent, because the money depends on how much time you make. So let's say you don't go babysit at all. If you're not babysitting, you're not making any money. Okay, after working 1 hour, you will have earned $5. 2 hours would get you 10, and 3 would get you 15. You might want to stick to cutting lawns, huh? You make more that way. After we have our table, it's kind of easy to go ahead and make your coordinate plane here, our ordered pairs, and let's plot that. And let's say, okay, 0, 0, here's my money. And here is the number of hours that I work. And let's just use this 1, 5. We can actually go by 5 if we want. 5, 10, 15, 20. So if I work 1 hour, I earn 5. 2 would give me 10. 3 would give me 15, and so on. We could connect this point, draw that, and then if we needed to, we could use that line to help predict if I work 20 hours, how much. And then what you're taking a look at in this table is the fact that every one of your non-zero values, at least, every one of your Y values is equal to the X value times 5, right? Which means your Y value is equal to your X value times 5. And so our equation for that one is Y equals 5X. Some nice Halloween colors there. Okay, let's take a look at one more example, and then after this one, we're going to study them all and see if we can come up with some things here. Now this one, it takes a little bit of work to figure out your unit rate. It's telling you that 7 candy bars cost $14. If you remember the fraction that we had the cost per candy bar, which means go ahead and take that cost amount and divide it by the number of candy bars, and it's costing you $2 for 1 candy bar. We're going to use 2 as our unit rate, or as our slope, which means if this is the number of candy bars and this is our cost, we don't pay anything. But as soon as we buy 1, we'll owe that a register 2. 2 would be 4, and 3 would be 6. Nothing fancy, right? And again, if I were to go and graph this, you would find that if we put our number of items on our X axis and our cost here, after buying 1 candy bar, well, first of all, here's my I don't buy any, I don't pay any, right? This is my origin. 2 would cost me 4, 3 would cost me 6, and I could extend this line, and I could keep going and going and going and use it to predict, right? And then that makes sense then that our equation for this one would be, okay, all of my Y values are just equal to my X value times 2. So here's what I want to do right now. I want you to take a look. I'm going to zoom out here for a second, and we're going to take a look at all of these graphs, because I want to ask you the question, what do these graphs have in common? Okay, so our first question is, what do all 3 of these graphs have in common? Let's look at them. This one here, and we got this one here, and then we've got this one underneath here somewhere. It's under here somewhere. Oh, it's above it, duh. So let's do this. I've got 3 graphs. What do you notice that they all have in common? Hopefully one of the first things you're thinking is they're all a straight line, okay? Because that's super important. Yes, they're all a straight line. Where do these lines start? They all started at the origin. Those are the 2 things that I was kind of hoping that you caught on to. So for right here, where it says, what do all 3 of these lines have in common? And you're going to fill these in because you should have these notes here. They're guided notes. And I want you to just go ahead and write, they are all a straight line, okay? They are all a straight line, meaning all of the points line up. You don't have one straight point here and there. So we call that linear, which is what we're going to be learning about. And then they all started at the origin. okay? At the origin, you're writing this down, and we know the ordered pair for the origin is 0, 0, okay? Those are the two things that I really wanted you to gather from that, okay? Because then the next thing I want to take a look at is, what do all three equations have in common? So let's go back to the equations and take a look at them. And I have, let's zoom this out here. I see a y equals 5x. I see a y equals 2x. And I see a y equals 10x. And so y equals 5x, y equals 2x, y equals 10x. They all look very similar. And that's because they are in the format. So let's go back and take a look at this. So what do all three equations have in common? They are all in the format of y equals some number and then an x, right? Every single one of them. And you saw how we created them. I didn't just put them in front of you and say, hey, take a look at this. So they are all in the format y equals x. And what we're going to write, and this is actually what we're going to start to discover a little bit. I want you to write y equals, and if you have different colors, great. If not, no big deal. Remember, we use the letter M to stand for slope. Slope is the same thing as your unit rate, right? So this is M, referred to as, we're not going to call it unit rate anymore because we're in our linear functions unit. It is now slope, and that basically means for one. Okay, for one rate, for one change, it's unit rate. Okay, so we know that all three of these graphs are straight line through the origin. They're written in the format y equals mx. And next we're going to take a look at what do these tables have in common. And this is a little bit of a trickier one. So we don't want to jump the gun here on this. Let's take a look at our tables. Let me zoom out here. Went the wrong way. So taking a look at these tables, I see this one, and this one. And what do you notice? Well, we said if our graph contains the origin, then what I'm telling you that you should notice is that each of your tables also contains that point. Okay, so it contains the point 0, 0. And the next one, well, actually you might be able to notice it. You notice how I drew this orange line on some of them? So I drew this orange little curvy arrow and I said, oh, that's just because you took this and did it times 5, times 5. This one was, right, it was like a times 2, times 2. And so a lot of kids, when I ask them to tell me what do the tables have in common, they usually say they contain the point 0, 0, and then they stop there, okay? However, I have a little note here that says we have to look a little closer into this one because just saying they contain the point 0, 0 is not enough, okay? Because they have more in common than that. And so what we're doing by trying to take a look at all three of these things that they have in common is we are trying to discover what it means to have something called a proportional relationship. Okay? This is what we're looking to define right now. And instead of me just coming out and telling you, I want you to kind of discover it on your own. So far I'm telling you all of these things that we've done, these examples are proportional relationships. But what makes them us able to say that? Well, you already told me. It's got to be a straight line and it's got to go through the origin if it's a graph. If it's an equation, it's got to be in this form. And if it's a table, it's got to contain the point 0, 0 and one other thing. And so in order to do this, we have two options really. So I'm going to be able to give you an easy way to check, two easy ways to check whether it is a proportional relationship or not. And so what we learned is, remember we talked about rise over run. And our rise was what our y value and our vertical movement, right, was. And our run on our coordinate plane was our x movement. So the y was the up and down, that's our rise. And the run was this way. So what I want you to do and you are going to be able to use a calculator for this, is we're going to take every single one of our y values and divide it by every single one of our x values and see if we get the same number. You shouldn't need a calculator for some of these, but I'll just show you a couple of them. So and this only works for the non-zero numbers. So ignoring 0, let's take a look at 12. We know 12 divided by 3, that's going to give us 4. Okay, good. Let's take a look at the next one, 24. We know 24 divided by 6, that's also going to give us 4. But I don't know, last time I checked, 32 divided by 9 does not give me 4. 36 divided by 9 does give me 4. So guess what? These numbers right here in my calculator are all different. Or this last one is different, which means that this is not a proportional relationship. This table right here is not a proportional relationship because when I divide all of my y's by my x's, I don't have that same, I used an orange arrow for that. I can't just say, oh, 3 times 4 is 12. 6 times 4 is 24. 9 times 4 isn't this. So the fact that this 932 is there means that this table does not represent a proportional relationship. It's not a proportional relationship. And so just saying that it contains the 0.00 is not enough, okay? Let's take a look at this next one. I don't even see the 0.00 anywhere, but it doesn't mean to count it out. It just might mean it's backwards somewhere. So let's take all of our y values and divide it by all of our x values. Let's take, and I can really tell by looking at this one, because if I take 5, that's half of 10. 3 is half of 6. 1.5 is half of 3, and 1 is half of 2. But let me just show you 5 divided by 10, because this is the process I want you to get used to. 3 divided by 6, you're going to get 0.5 for all of them. 1.5 divided by 3, and 1 divided by 2. And I really want you to just see this. See how all of those are 0.5s? Then this is a yes. This is, so this you will say, yes, this is a proportional relationship, okay? Because it met that qualification of having that by the same. So I want you to take a look at this third example here, and let's see if you can decide whether it's a proportional relationship. Yeah, it contains a 0.00. Let's see, 5 divided by 10. 5 is half of 10. 8 is half of 16. 9 is half of 18. And 11 is half of 22. Okay? So this is also a proportional relationship. I want to take a look at this last one, and guess what? This one's easy. Because what did I say up here? In order for it to be a proportional relationship, the first qualification it needs to meet is that it has to have a 0, 0. And this doesn't. This has a 0, 4, which means if I were to go to plot this, I'm not even starting at the origin. I'm starting at 0, 4. It might be a straight line, but it's not a straight line through the origin. And so in order for us to be able to say this is a proportional relationship, it doesn't even meet the first qualification. So this one we would say, no, this is not a proportional relationship, okay? Now, I mentioned that you had 2 options to help you figure out whether it's a proportional relationship. And the first one was if you multiply, actually we're not gonna go that direction. We're gonna divide all of the y's by the x's, and if I get the same number, the same factor, I guess you could say, then yes, it's proportional. Okay, because that's like saying every lawn I mowed was $10, and it was never sometimes 8 and sometimes 5. It was 10 every single time. The other way, I just kind of, I don't want you to rely too heavily on it. They say you could use cross products. Cross products means if I take any 2, and I would have to do it for the whole table really, and multiply them, I should always get the same. So 10 times 3 is 30, and so is 6 times 5. 3 times 1 is 3, and so is 2 times this. Let's take these two. 10 times 1 is 20. 5 times 2 is 20. And that's an example. You could take any 2 pair, cross multiply those diagonals, and if you get the same product, it should equal each other. Let's show how that doesn't work up here. So if I did 0 times 12, 3 times 0. So then let's take 3 times 24, which should give you 72, and 12 times 6 is also 72. Let's take a look. Now that worked, but remember, you have to check it for all of them. I want you to take a look at the point that made it not proportional. There was this 9, 32. Let's do 9 times 24 and see if that equals 32 times 6. So 9 times 24 is 216. 6 times 32, it's not. So the cross products don't equal each other. So that is just another way to show you. And I'm just going to write check cross products. If you multiply diagonals and they give you the same product, it's proportional, okay? We might rely a little more heavily on the y divided by x just because it's going to help lead us into some things later. Okay, let's wrap this up. I want you to, this is the purpose of this whole assignment, was learning about what a proportional relationship is. A proportional relationship is a straight line through the origin that can be written in the form of y equals mx, contains the point 0, 0, and has the same factor relationship from a table. So let's take a look at this. Is this a proportional relationship? Is it a straight line through the origin? No. So for this one, you're going to say, nope, not a proportional relationship. Why? Because it doesn't contain the point 0, 0. Automatically disqualifies it, okay? Is this a proportional relationship? No. Is it written in the form y equals mx and that's it? No. You got this little, so let's kind of say that this is what makes it not a proportional relationship. This disqualifies it from being a proportional relationship. So this one is also a no because it's not written in the format. And right off the bat, this is also not a proportional relationship because it can't contain the point 0, 5. It's got to contain the point 0, 0. So these are non-examples of proportional relationships because they don't meet the criteria that you just told me they had to meet. So let's look at these 3. Is this a straight line? Yes. Does it go through the origin? Yes. So this is a graph of a proportional relationship. It's all it needs to meet for a graph. Is this equation an example of a proportional relationship? In other words, does the equation fit the format y equals mx? Yes. Okay. And then is this table a proportional relationship? Does it contain the point 0, 0? Yes. Does it have the same factor when I divide? If I divide 2 by 20, I get 10. If I divide if I get 20 divided by 2, I get 10. 30 divided by 3, I get 10. 50 divided by 5, I get 10. And because they all give me that same factor, yes, this is proportional. So what you're going to be asked to do is basically, to start us off pretty simple, is identify proportional relationships from a graph, from an equation, and from a table, and your answers will literally just be yes or no. If it's a no, you're going to tell me what disqualifies it from being a proportional relationship. Okay, that's it.